Hello everyone, my name is Marcelo Vinícius and today I will be presenting to you our research entitled Direct Instantaneous Torque Control of Switched Reluctance Machines for Low Torque Ripple Regenerative Braking. This research was developed in Unicamp in a partnership with Ontario Tech University in Canada. In our agenda today we have a brief introduction about the SRM and its principles. We will also talk about the SRG dynamics. Then we will discuss the motoring mode and generating mode of the direct instantaneous torque control. After that, I will present to you some of the simulation results and some of the experimental results, and we will finish it with drawing the conclusions and talking a little bit about the possible future works that we can do in this research. Talking a little bit about the SRM advantages and disadvantages, we can observe that the SRM is a doubly salient structure, as you can see here in the image on your right, and it has only windings on the stator. And when these windings are energized, they attract the closer rotor pole. And this principle is known as minimum reluctance principle. The principle of operation of the SRM is what gives its advantages and disadvantages. For example, we have a high fault tolerance in these machines, they are rugged machines, and they also present high torque density, among other things. And about the disadvantages, we must cite the elevated torque ripple, the nonlinearities caused by the driving principle, and the high acoustic noise. Besides, the torque ripple minimization is the focus of this research, so there are many techniques in the literature that can be found. For example, we have current profiling techniques in which we use torque sharing functions to divide the torque among the phases. Another example is the direct torque control, in which we adapted the control method from the induction machines to the SRM. And we also have the direct instantaneous torque control, which is the object of study of this research. On the literature, it is possible to encounter a lot of papers and theses and research about the motoring mode, the DITC. However, when we are talking about the generating mode, they are not so much out there. So this research is focused on the generating mode, the DITC. Moving forward for the SRG dynamics and working principles, we have the electric dynamics of the SRM. So here in equation 1, we can see three terms. The first term relates to the resistive voltage drop in the resistance of the winding. The second term represents the voltage across the inductance of the machine. And the third term is related to the back EMF, which plays an important role in SRM because it defines the voltage regulation according to the speed and current. In other words, according to the operation point. About the electromechanical dynamics, we have equation 2. And if we consider that there is no commutation, we can describe the torque as the last part of the equation 2, in which we can see a quadratic relation with the current, meaning that independently of the current's direction, the torque will be produced in the same direction. However, if we look at the inductance derivative according to the position, if the inductance derivative is positive while the motor is being driven, then the operation will be taken in the motoring mode. And if the inductance derivative is negative while we are applying voltage in the machine, the operation will be taken in generating mode. Now talking a little bit about the motoring mode, the DITC. The DITC in general is a closed loop torque control with double band hysteresis, and in which we are focusing on control the torque error. So we have different objectives for this controller. The main objectives are to minimize the torque ripple, to avoid the hard chopping, to prioritize the incoming phase for torque production, and to keep freewheeling state for as long as possible. All these objectives are focused on maximizing the efficiency and minimizing the torque ripple, while not producing negative torque while in the motoring mode. We have state machines that can summarize the DITC. For example, in the figure on your left, we have the state machine for the incoming phase, while the figure on your right displays the state machine for the outgoing or single conduction phase. Here we can see that the electromagnetic torque error is compared with thresholds. We have higher thresholds, lower thresholds, and medium lower and medium higher thresholds. According to these equations, a different state will be applied on the SRM phase. So, if the state 1 must be applied, it means that we'll have to apply positive voltage to the winding, as the figure indicates here in the bottom. If the zero state is to be applied, then the phase will be short-circuited. And once the -1 state must be applied, it means that negative voltage must be applied on the phase. Moving forward for the generating modes, here the objectives are a little bit similar, but there are a few changes. For example, we have also the objective of minimizing the torque ripple. On the other hand, we want to maximize the absorbed energy, so we prioritize the demagnetization state instead of prioritizing the freewheeling state. Also, we prioritize the incoming phase for torque production because we don't want to produce positive torque while in the generating mode. Similarly, we avoid magnetization state to maximize efficiency. At the generating mode, we also have state machines, as we can see here for the incoming and single conduction phase and for the outgoing phase. The logic of applying voltages is the same as in the motoring mode. Now that we have discussed the generating and motoring modes of the DITC, let's move forward to talk about the machine we are using. The SRM used in the simulations and on the experimental results was a 1500 watts nominal power with 96 radians per second as a base speed. The voltage of operation was between 30 and 80 volts, and the thresholds used for the DITC was always between 0.25 and minus 0.25. The simulation was developed in MATLAB Simulink environment, and it can be described as the block diagram in the screen right now. So we have an asymmetric half-bridge converter driving the SRG with a DC voltage applied to it. The DC voltage here is represented as a battery, so we can observe the state of charge and determine if it's working, if the machine is working as a generator or as a motor. Also, we have the DITC core. So in the DITC core, first we have to estimate the torque through the current measurements and position. After the electromagnetic torque is estimated, we compare it with the reference value and parse it through the hysteresis torque controllers. With that, we use the switching logic along with the switching angles to generate the switching signals. The variable we are looking at here is the torque ripple, and the equation used to calculate it in real time is the equation described in 3. Note here that we use the modulus operand to guarantee that the value is positive, so we don't have numerical errors while employing this in an experimental setup. Then, to verify the motoring mode, a test was performed at 60 radians per second and 1.88 Newton meters as a load torque. In the figure, taking a closer look, we can see that the soft chopping was achieved, as we don't see the positive voltage going to the negative voltage in one step. Also, the electromagnetic torque is regulated inside the hysteresis band, and the state of charge is decreasing, characterizing the motoring mode. Besides, we calculated the torque ripple to be always smaller than 8.06%. Going back to verify the generating mode, we performed the test at 60 radians per second and a load torque of minus 3.08. Once again, taking a closer look here, we can see that the demagnetization is always preferred, and the magnetization is only used when it's absolutely necessary to increase the torque. The electromagnetic torque was maintained inside the hysteresis band, except for one point here where we lost a little bit of torque regulation. Nonetheless, the state of charge is increasing, showing that the generating mode is in operation. Also, the torque ripple was always maintained lower than 11.2%. Now that we have verified the simulation results, let's talk a little bit about the experimental results. So, to verify experimentally the proposed control system, we developed an experimental bench in Unicamp. The experimental bench is composed by two motors, one SRM and one DCM for the load torque. Also, we coupled the two machines through a torque transducer, and we are using an encoder to verify the position of the machine. There are two signal conditioning boards to control and process the signal of the sensors of both machines, and there is also one symmetric half-bridge converter for the SRM and one half-bridge converter for the DCM drive. There are also two bidirectional choppers to control the DC link voltage of the SRM, as you can see here at the figure, and for the DCM, as you can see here at the figure. We also developed two HMIs in LabVIEW software to control separately both machines. We can control the load torque and the speed of the SRM. This bench was developed because it gives us a lot of versatility in experimenting with the proposed system, and it will be further used in future works. In the first test, to verify the motoring mode, we performed a test in 400 RPM and with a load torque of 4 Newton meters. We can see at the experimental result figure that good torque regulation was achieved while the electromagnetic torque was maintained inside the hysteresis band. The torque ripple was calculated to be always lower than 14% throughout the entire experiment. To verify the operation in the generating mode, we performed two tests. The first test was at 700 RPM and minus 4 Newton meters load torque. Note here at the figure that there are current spikes at the end of the conduction, and it's due to the turn-off angles which are higher than the simulation results. We wanted to show this effect to show how important it is to choose the correct turn-off angle. Another point we tested was at 400 RPM and minus 4 Newton meters load torque. You can see here that there are small torque dips during the commutation, as we observed on the simulation, so it's perfectly normal, and the torque ripple was always lower than 19% while being maintained inside the hysteresis bands. I would like also to highlight that these small differences in the torque ripple calculated in the experimental results and on the simulation results happen because of current noises and errors in the machine model used to estimate the torque. Moving forward, we can say that in this paper we proposed a DITC for regenerative braking mode, and we achieved good torque regulation in both generating and motoring modes. We also saw that the experimental torque ripple was always lower than 19% in generating mode and lower than 14% in motoring mode, which proves that the regenerative braking was achieved while maintaining the torque ripple at a low level and showing that the proposed system has a capability for applications in aerospace and automotive industry. With that, we finished drawing our conclusions, and we can talk a little bit about the future works. So, this research could develop in many different directions. For example, we could make a DC-link voltage regulation to determine which voltage would be applied to the SRM according to the operation point. Also, a more broad analysis could be made about the hysteresis band choices and about the operation point influence over the proposed torque controller. The driving angles could be optimized, and some sensorless operation could be employed to make the proposed system more affine with the automotive and aerospace industry. So, I hope you all enjoyed this presentation. I'd like to thank Colbap for having me here. It's always a pleasure to be part of the Brazilian Power Electronics Conference. I'd like to thank our funding parties, which were the São Paulo Research Foundation and the CNPq. A deep consideration for my partners at Power Electronics Lab, which helped developing this research, and also to the collaboration we did with Ontario Tech University at Ontario, Canada. Once again, thank you all for watching.